Okay, so last time when I talked about relative illumination, it was a little bit of a satire. So today I'll try to be a little more serious. Relative illumination is the brightness profile across the image plane. It's called illumination, but it's more like irradiance profile from the center of the field of view to the edge of the field of view. So if you call out the plot in lens design program like Zemax, for example, you see a profile that you may expect a profile like this because you're thinking of probably the cosine fourth law, but that's just one part of it. It's more than that because you can tune the lens design to make this profile flat and uniform. But if you're new to lens design, and you do a Google search. Let's say you go to Google Gemini, do an AI prompt search with a prompt in lens design. How do I produce a flat relative illumination curve? You get a whole bunch of stuff, and you can see here I've blanked out the references here because these references they refer to companies, and I have nothing against the companies. I just want to blank it out and talk about how the AI search very inaccurately summarizes everything because they give you a whole bunch of facts. They're facts, they're factual stuff, but there's no link, conceptual link between them. It says things like, okay, try creating image space telecentricity. Well, you don't really have to have image space telecentricity to have a flat curve, okay? And then it says pupil aberrations, pupil coma. Try to control the pupil coma, which is correct. Then it says try to control the distortion, which is also correct, but pupil coma and image distortion are related, okay? So the real way of doing this is to examine the equations for relative illumination at low aperture. Okay, and you can do it two ways. One way is to think of in terms of the object space, and one way is to think in terms of the image space. In the object space formulation, relative illumination, this R here is relative illumination between 0 and 1. You've got all these variables here. You've got chief ray angle in object space, right? And then you've got this ratio here, which is the ratio of the off-axis entrance pupil area to the on-axis entrance pupil area. And at the bottom, you've got D, which is distortion, which is a curve, right? This distortion here, D is fractional, which means if you have negative 5% barrel distortion, D will be negative 0.05, all right? And then you've got another quantity. You got the Y field times dy. That's differential distortion. Okay, I coined that term for this equation, which I derived in 2017. I'm not the first to derive an equation that looks something like this. Max Rees did it in 1930 something or 1940 something. I can't remember. He did it in a different form. It was a little bit hard to read, so I redid it independently in this form, which is I think it's a little easy. And you can write this in terms of for an object at infinity as well. That's the angle. You just have to go to my profile, go to my website, click on research, and you can read a whole bunch of references there on papers that I've written on relative illumination, and you'll find that some of them are even open access. So anyway, in the image space formulation, you've got the ratio of the off-axis exit pupil divided by the on-axis exit pupil area, all right, times cosine fourth theta prime, where this theta prime is the chief ray angle in image space, right? And these two equations, they compute exactly the same thing because of flux conservation, right? So you can use one or the other. And why look at the equations when you can actually have a merit function operand to control relative illumination? Why is because when you look at these, especially the object space formulation, you can tell whether or not you're over constraining your system, right? If you are already constraining relative illumination, you may want to think about constraining distortion in some other way, right? Or the entrance pupil aberrations in some other way. So there you go. And that's what I wanted to share. Thank you very much.